This is Trig 3.7, rates of change. Rates of change are exactly what a slope is. Basically, when you do slope, you're doing rate of change. You're doing the rise over the run, or basically the change in y over the change in x. That's exactly what you're doing for slope. So we're kind of trying to figure out slope here. When a rock is dropped from a high place, the distance the rock travels is given by the function 16t squared. A lot of you guys are taking physics right now, and so you know that the 16 comes from the acceleration due to gravity, which is in feet per second. It's 16 feet per second, or 9.8 meters per second squared, I guess. So that's where that equation comes from. But they go ahead and give us a table for it. So they're saying at a time of 0, the distance that's been traveled is 0. At 1 second, the rock has gone 16 feet. At 2 seconds, the rock has traveled downward at 64 feet, and so on and so forth. They give us this table, all right? So they're saying the average speed, if I'm trying to find the average speed, okay, they give us this equation for it, which basically says for average speed, we're trying to figure out the distance that it's traveled in the amount of time that it's traveled. Okay, I can do a bunch of different average speeds here, all right? And the average speed from 1 to 2 seconds is going to be different than the average speed from 2 to 3 seconds, right? From here, it's not traveling quite as fast because it hasn't been traveling quite as long, but from 2 to 3 seconds, it's started out faster here, and so the average speed is going to be faster. Even though it's only going 1 second between each one, it's going to be faster in this time interval because it's been traveling 2 seconds already. So if that kind of makes sense, they're going to illustrate that down here with this problem. So they want to know the average speed from 1 second to 4 seconds. So we're starting with 1 second and we're going to 4 seconds here. 1 second is at 16 and 4 seconds is at 256, okay? If you remember from the formula for slope, like y2 minus y1 over x2 minus x1, that's exactly what you're doing. D of b minus d of a means the y-coordinates, b minus a is the x-coordinates. So if you're going from 1 second to 4 seconds, you basically do 256, which is the y-coordinate here, minus 16 over 4 minus 1. And that is 240 divided by 3, which is 80 feet per second. So on average, it is going 80 feet per second from 1 second to 4 seconds. Okay, from 2 to 4.5 seconds, so we would do 4.5. The y-coordinate there is 324 minus 2 seconds is 64 over 4.5 minus 2. 324 minus 64 is 260 divided by 2.5, and I need a calculator. 260 divided by 2.5 is 104 feet per second. So you can kind of see how, like, different time intervals, it's traveling faster or slower, and that's just because, like, you're not increasing your speed at a linear rate, right? It's quadratic. So this is what 16t squared looks like. You're starting off going really slow, kind of, and then all of a sudden you just like go really fast when you get up to the end here. So the number of seconds, the more seconds you've been traveling, the faster you're going to go. So those rates of change won't be exactly the same because it's not a linear function. It's not doing things linearly. So average rate of change, f of b minus f of a over b minus a is exactly y2 minus y1 over x2 minus x1. Okay. So now they give us the equation. A balloon is being filled with water. Its approximate volume is given by x to the third power over 55. Right? They do not give us a table, but the easiest thing to do is go ahead and write a table, especially when they give you points. So they want us to know, find the average rate of change of volume as the radius increases from 5 to 10. So the radius is like my x-coordinate, and the volume is like my y-coordinate. Volume, this is radius. Okay. So as my radius changes from 5 to 10, what's the volume doing? So in order to figure out what the y-coordinate is, I need to plug that into the equation. 5 to the third power is 125. Let me just plug that into my calculator. 5 to the third power divided by 55. I'm just plugging this into this equation and getting out the answer. So that is 2.27. I'm just going to do 2727. We'll round to 4 decimal places. Okay, and then I'm going to do the same thing with 10. 10 to the third power is 1,000. But we'll go ahead and just type it in regularly. Divided by 55 is 18.1818. Okay. Now they want to know, find the average rate of change. So we do the y coordinates subtracting. 18.1818 minus 2.2727 divided by 10 minus 5. Y2 minus y1 over x2 minus x1. Right? So 18.1818 minus 2.2727 divided by 5 is 3.18. That volume is increasing at an average of 3.18 gallons. No, x is the radius of the balloon. Gallons per second, minute, second. 5 to 10 inches. It doesn't say. A balloon is being filled with water. It doesn't say how fast we're doing. I'm going to say gallons per minute. So that's the average that we're doing. 3.18 gallons per minute. All right. So there is that. Okay, manufacturer's cost. This really is going to illustrate what they were talking about with how fast things are going. So the difference from 1 to 2 seconds, it's not traveling at the same average speed it is from 2 to 3 seconds. And they're going to really illustrate that down here. So a small manufacturing company makes specialty office desks that cost in thousands of dollars. Of producing X number of desks is given by this equation. Blah. Find the average rate of change of the cost. Okay, so from 0 to 10 desks. I'm going to go ahead and make a table here. X, Y. I'm going to put everything that we need. So I know that I'm going to need a point for 0. I'm going to have to figure out the Y coordinate that goes with 0, 10, 30, and 50. I will need all of those. Okay. So we're going to plug those into that equation and get an answer. If we plug 0 in, 0 to the third power, 0 to the second power is 0. All of that stuff's going to cancel out, and 5 is the only answer that I have left. So that one's easy to do, but let's plug in 10. So I'm going to do 0.0009 times 10 to the third power minus 0.06 times 10 squared plus 1.6 times 10 plus 5. Okay, and I get 15.9. Okay, if I do 30, I have a really nice calculator that I can do. I can hit the up arrow and hit enter, and I can just go ahead back through and change all these 10s to 30s. So I'm just going to do that, then I don't have to retype everything in again. Enter. I get 23.3. And I'm going to do the same thing for 50. 50. What did I not change one? There we go. There we go. Enter. So 47.5. 47.5. Okay. So from 0 to 10. 0 to 10, the y coordinate for 10 is at 15.9. I'm going to subtract 5. I'm going to do that over 10 minus 0. Which gives me 15.9 minuse 5 divided by 10, basically, is 1.09. Okay. Over here, let's do, so the next one is 10 to 30 desks, which would be like these two coordinate points. So I do 23.3 minus 15.9, and I divide by 30 minus 10. Okay. 23.3 minus 15.9 divided by 20 is 0.37. And the last one is 30 to 50 desks. Okay, so that's going to be these two sets. 47.5. Again, you're just basically finding slope here. 23.3 divided by 50 minus 30. Okay, now notice that from 10 to 30 desks is the same increase as from 30 to 50 desks. But I'm guessing that these two numbers are going to be the same because it's not a linear function. It's not going to be up 0.3 or 0.37 every time. So 47.5 minus 23.3 divided by 20 That's going to be, oh, did I do that right? Yeah, 1.21. Sure. 23.3 minus 15.9. I think I did that right. No, I did not do that right. No, yes, I did. I'm just checking these back again. Hold on. 15.9 minus 5 divided by 20. Yeah, I did this right. I did this right. So there is that. So the average, the average rate of change of the cost. So the average cost of a desk is 1.09, basically in the interval from 0 to 10. In the interval from 10 to 30 desks, they're costing an average of 37 cents or whatever those are. And then from 30 to 50 desks, it's 1.21. So basically, if I'm going to do this, I probably am going to want to buy some amount from 10 to 30 desks because those are going to be, on average, cheaper. Okay, and the reason why I was confused because I thought, well, this is probably from 30 to 50 desks should be the cheapest, right? Because if you go into a store and you buy it in bulk, it should end up being the cheapest. But our problem is our function is not quadratic, it's cubic. So it's going to go up and then it's going to come down and then it's going to go back up again. That's what a cubic function does. So here might be at this point, or maybe even here, 0.37 is going to be the lowest and then it's going to go back up again at the 1.21. So that's why I was confused. All right, so there is that. Let's go to the back side. The rate of change of temperature. The graph shows the temperature function of F during a particular day. The temperature at X hours after midnight is whatever. What is the average rate of change of temperature? Okay, so 4 a.m. is here and noon is here. So they want to know the average rate of change. So I would say that 4 a.m. is probably at 40 degrees, and noon, oh my, where's noon at? Noon is about there. I'm going to say that that's maybe about at 64 degrees. So 4 a.m. is at 40, noon is at 64. So we're going to go 64 minus 40 over noon, which is 12 minus 4 is going to be 8 hours. I'll write it out. 12 minus 4 is 24 over 8, which is 3. So on average, in that time interval, it's raising 3 degrees per hour. Okay, and then from 3 p.m. to 7 p.m., my 3 p.m. is right about here. It's not quite at 1600 hours. That's what 4 p.m. would be. This would be 4 p.m. 20 p.m. would be 8 p.m. So 3 p.m. is about probably at the highest point, which I'm guessing is 68 degrees. And 8 p.m. is about there. Let's call that 50. Let's call that 53 degrees. 53. So okay, hold on. 53 minus 68 over 8 p.m. minus 3 p.m. That's 5 hours. 53 minus 68. I can't even do that. My brain's not working. Negative 15. So it is going down 3 degrees per hour, basically, on average, is what that is looking like. Okay. So again, those are just estimations. I might not have been exactly perfect, but it's going to be somewhere close to 3 and negative 3. Okay. All right. Last thing, secant lines and average rates of change. So what we're looking at, basically, when we're going from 4 a.m. to noon. Oh, it wasn't. No, it wasn't. At noon we said was 64 degrees. Well, we were off a little bit. And let's see, 4 a.m. we said was 40. That one we got right. But noon was actually 58 degrees. Whatever, we don't care. Basically what you're doing is, even though the temperature starts out by kind of leveling off, and then as soon as we get to like 9 a.m., this is probably sunrise, okay? As soon as we hit the sunrise, the temperature is going to go up significantly. But what we're doing by saying that this is an average of 3 is basically by like putting a linear function. So we're saying that it basically follows this linear function and continues to go like that, right? That's basically what a secant line does. Instead of showing you that it curves like this, we're basically like showing the average is a line, all right? So computing the average speed by using a formula. Find a formula for the average speed of a falling rock from a time of x to time x plus h. Use the formula to find the average speed from 3 to 3.1 seconds, okay? Average speed of something falling is 16 t squared. We know that from the beginning, all right? So find the formula for the average speed of a falling rock from time x to a time of x plus h, okay? So what we're going to do when we do that is we need to have the y coordinates. So it's like y1 minus, or y2 minus y1 over x2 minus x1, okay? This stuff's going to be a little bit more confusing than the above stuff. But the y coordinate, you figure out the y coordinate. If your x2 is x plus h, and your x1 is just x, okay? They're saying from a time of x to a time of x plus h, all right? X plus h is my second coordinate. I can do that on the bottom. X plus h minus x, okay? And then on the top, your y coordinate is basically like f of x plus h minus f of x, right? y2 minus y1. The function with x plus h plugged in and the function with x plugged in, okay? And we know that our function is 16t squared. So I might as well write this as 16 times x plus h squared, because x plus h is my x. I'm replacing that with t, minus 16x squared over x plus h minus x. Yuck, yuck, yuck. Okay, this is going to feel really confusing. If you're confused, it's okay. So on this top right here, 16x plus h squared, I'm going to leave minus 16x squared over, but I'm going to take this x and I'm going to subtract that x, so I have an h there. This is what your equation is going to look like for the average speed of a falling rock from x to x plus h seconds, okay? Now, if I'm going from 3 to 3.1 seconds, that is your x plus h is going to be your 3.1. So 16 times 3.1 squared minus 16 times 3 squared is what you have there. Your h is what you're adding. So if you think of x as being 3.1 is your h, what you're adding. So 0.1 is the bottom part down here. And this formula is very ugly. It's hard to come up with on your own. But as soon as you have this, you can very easily just plug stuff in and you don't have to do the whole process all over again. So let's just figure out what that is. 16 times 3.1 squared minus 16 times 3 squared divided by 0.1 is 97.6 is the average that this rock is falling. The average speed that the rock is going from 3 to 3.1 seconds is 97.6. Okay? And that is in, I don't know, feet per second? Feet per second is how fast that rock is traveling. Okay? All right, the formula for the difference is this guy right here. I'm going to go ahead and skip this last example, and that's all you have, okay? I'll kind of go over this last problem again tomorrow, and we'll talk about like rates of change and how they are different between time periods, but that's basically what you're doing is finding slope between 2 points, okay?